What is it? Conservation of mass and continuity. When we say conservation, what does it mean? Or to conserve, what does it mean? What? To retain. Yeah, that's the word. Preserve, maintain. Okay. Yeah. It's just like to save something. And that's like the word. And that's like the actual word. To save something. You save money. When it comes to wildlife, you don't save wildlife. Let's say you don't want some species of animals to go extinct. So you want to preserve them. You don't say you want to save the animal. What do you do there? You conserve them. Yes. The word conserve is synonymous to save, but used in some instances. Think of this. When it comes to conservation, generally, what comes to mind? From physics and this thing. When we say conservation, what comes to mind? Energy. So what the law of conservation of energy says that what? The same thing happens here. Think of this. The law of conservation of mass states that mass can neither be created nor destroyed. The law of conservation of mass states that mass can neither be created nor destroyed. Please always note this stuff. When they say something conservation, state the law. Don't stress. It means that that thing cannot be created nor destroyed. Of course, except in nuclear processes. Yes. When you have nuclear fission and nuclear fusion. Right. In that case, then you can create mass, you can destroy mass. So, the law of conservation of mass states that mass can neither be created nor destroyed except in nuclear processes. That's it. Except in nuclear processes. Full stop. Take a paragraph. Let's get a very short note. Do some stuff, take some past vision, you're done. From this concept, we can obtain the equation of continuity. Which states that within any hydraulic system, the discharge flowing in within any hydraulic system, the discharge flowing in, the stored volume in bracket control volume. The stored volume in bracket control volume and the discharge flowing out must be balanced. The discharge flowing in, the stored volume, also called control volume, and the discharge flowing out must be balanced. Please take this down. Must be balanced. Alright, so you have this for your diagram. Mass flowing in, control volume, mass flowing out. Alright. Do you have this, please? is also a past question answered. I think the one I like doing is that I like answering past questions. So that by the time you give past question, you open it there, question one already answered here, it's already answered. So you're also doing it, you also answered past questions and everything. Alright. So it means that is mass entry per unit time. That's this. The mass entering in, comma, the controlled volume or the stored volume, and the mass going out must be balanced. So that is mass entering in should be equal to mass going out. Of course, this said mass entering per unit time, that's mass flow rate, m dot, is equal to mass leaving per unit time, that becomes m dot. Just to separate them, let's call the one entering or flowing in as m1. Let's call the one leaving as what then? m2. So I have m dot is equal to m1 dot fine. m1 dot equal to m2 dot. But what do we know? Hold on now. But what do we know? But we know that mass flow rate, from the relationship between mass flow rate and discharge, we know that mass flow rate is equal to mass density times discharge. We have this. And we said discharge is the product of area and velocity. That means for this case here, we have that mass flow rate is equal to mass density times this one here, we said is area times velocity. That's how we express this. So if I expand this, it means that the mass flow rate is equal to mass density times area times, perhaps let me use U for this. Let me use U for velocity instead of V. If you want to use V, still fine. It becomes times U. If I substitute this condition into this, I will have that. So therefore, it means that M1 dot being equal to M2 dot can be written as this one becomes rho 1, A1, U1, that's for 1, is equal to, for this one becomes rho 2 of course, A2 of course, U2. So we have this. But there's something we know from the concept of density. We said mass density is what there is constant. Abi? Yeah, we said this. We said mass density of any fluid is constant. So if the same fluid is flowing through any conduit or any pipe, the mass density is always constant. If it's constant, what does it mean? It means that rho 1 is equal to what there? Rho 2. And from mathematical concept, if I have the same term multiplying both sides, I can cancel 2 of us. So this one here, and now cancel this, since they're the same thing. So hence, I'm left with A1 U1 is equal to A2 U2. So we have this. This becomes the equation of continuity. A1 U1 is equal to A2 U2. This is called the equation of continuity. Please take note. A1 U1 equal to A2 U2 equal to A3 U3 is called the equation of continuity. Now we have two of these. Alright. Take that please. The above is called the equation of continuity. It provides a means of calculating the velocity at different points in a system. It provides a means of calculating velocity at different points in a system. Alright, let's do some past questions. We are done for the learning today. Let's now do past questions for the time we have left. Please check 2014-2015 fluid mechanics past question. Check your question, please. It says a pipe 100 millimeters in diameter expands to a diameter of 150 millimeter, then increases to 250 millimeter. It is known that the velocity in the 150 millimeter pipe is 1.5 meters per second. Full stop. determine I, the discharge in the pipeline, II, the velocities in the other pipe. When it comes to this stuff, please, your first task is to draw a diagram. Please listen. In this stuff here, your first task is to draw a diagram. The diagram varies depending on the question. In this particular question here, they said the first thing that I have is 100 millimeter. From 100, it expanded to what there? 150. From 150, it increased to what there? 250. So small, bigger, big, and then bigger. Right. So look at it. Please, there are different diagrams to this. Look at different diagrams. In some cases, say the pipe breaks. If it breaks, look at how you draw that one too. But for this one here, I'm drawing from 100. From 100 to 150 to 250. So that means the 100 millimeter diameter pipe becomes your smallest. So I'll start from somewhere here, here to here. This one first. This one expands to this. Okay. So from the 100 to 150. Let me draw this better. 100 to 150. From the 150 to the 250. From here, it goes to 250. You see why I draw them and make them bigger. Okay. Let's sketch this better. Alright. So this is your first task, sketch a diagram. You have this. What next? What next? You section them. This pipe has 3 sections. It has the 100 millimeters, it has the 150, it has the 250. So section is like this, this, and this. So we first the section using what's it called? Using what's it called? Short dashes, like short, just like this. So we prefer to use it this way to show the section of the pipe. So call here section 1, call here section 2, call here section 3. You know how we do? You know how we represent diameter in engineering? For section 1, it becomes this. So phi 1 is 100 millimeter. Okay, do it this way. You have this. That means diameter of section 1. This one next, diameter of section 2, the same is 150 millimeters. And I think that's this semester. This semester, this will be doing engine drawing. You do tolerance this semester, me? Yes. Tolerance value and how to write what's it called? How to write what's it called? Diameter. You take this semester. Right. Tolerance, those knots and those stuff. What do you use next semester? This 3 is 250 millimeters. You have this. Alright, so you have section 1, section 2, section 3. Just for uniformity's sake, let me use, instead of straight so let me use straight line instead. It's not the same again. So what's this stuff? What's this? What's this? If you look at what's it called? If you look at where, okay fine, I want to join a pipe. I want to join 2 pipes in which one of them has a big hole or a big diameter, and the other one has a small hole. How do you join them? Huh? Yeah, so you know what the sucker looks like, right? Has at one end it has a big mouth. I mean, yeah, that's what you have here. That's the same case here. So this is what we present as this. So that's the concept here. This is just a pipe with bigger diameter. So at this point, when you have this stuff now joining this and this, same thing here. This one has a bigger size joining this and this. So that's why the concept here. So I have this. Okay. So I have this for the diagram. Let's look at parameters there. Let me list out giving parameters. So given number 1, diameter of section 1 D1 is equal to 100 millimeters. Convert to meters, divide by 1000, 0.1 meter. Number 2, diameter of section 2 D2 is equal to 150 millimeters. Divide by 1000, 0.15 meters. Number 3, diameter of section 3 D3 is equal to 250 millimeters. Divide by 1000, 0.25 meters. So I have these 3. What else? They said it is known that the velocity in the 150 millimeter pipe is 1.5. 150 is for section 2. So hence, I'm also given by 4, U2. That is the velocity in section 2, which is this, as equal to 1.5 meters per second. So I have this. Your task is to calculate the discharge in the pipeline. That's number 1. Number 2, the velocities in the other pipes. Alright. Please get a better one. Let's work together. Alright, number 1. Discharge in pipeline. Discharge in the pipeline. What do we get? What do we get next? From here, now you now see from continuity, from the equation of continuity, what do we have? We have that discharge Q is equal to A1 U1 equal to A2 U2. Since there's a third section equal to what here? A3 U3. So I have this. That means from any of these 3, you can find discharge. So I will use that discharge Q is equal to, since I have since I have velocity for pipe 2, I'll use A2 U2 instead. So discharge becomes A2 U2. Do I have U2? Yes, 1.5. Do I have A2? Not yet. Can I get A2? Yes. Record that area A is equal to what there? 5d squared under what? 4. That's in terms of diameter. Or convert to radius first. Then use pi d squared. Whichever one. For A2, I'll have that A2 is equal to pi into D2, pi D2 squared all over 4. And that gives you pi into D2. D2 is what? This one here. Becomes 0.15 squared all over 4. Please give me value. So A2 is equal to, give me value. Punch anything there, what do you have? Zero point 0177 units meter square is area meter square. So let's get discharge. So therefore, discharge Q is equal to A2 U2, and that's equal to A2 is 0.0177 into U2. U2 is this. That's 1.5. Please expand this. We have that discharge Q is equal to, what do you have? 0.0266 what? 65 units. Hello, unit. meter cube per second. They've got to the I part. Find the discharge in the pipeline. We've got the I part. I part. I actually define what we with. Okay, velocity in other pipes. So velocity in other parts. In other parts. When we say velocity in other parts, the one given is U2. So if you say in other pipe, means you find what there? U1 and what? U3. That's what's left. So that is find U1 and U3. And that should be easy. With same velocity, with, sorry, yeah? Yes. Right. So in this case there, we said when you had different velocities, that was take the mean velocity. So how come this way not taking mean velocity? The idea is simple. When we say take, listen, when we say take, let's use something you can relate to. Right? The class is the way to. Let's say I have water coming out from here. I want to pass here, and I'm using a small pipe, or a pipe that has a small hole like this. And in this same instance, I'm using a pipe that has a bigger hole. Now, here's the fact: the rate at which water is flowing here will be different from the rate at which it's flowing here. Two of us. Between the smaller pipe and the bigger pipe, which one will flow faster? Smaller or bigger? Huh? Smaller will go there, flow faster. Now listen. In this case now, we are assuming that water is flowing from here and here at the same rate. But if I look at this now, since I'm using a smaller pipe here, water will flow faster here than here. In this case here, if water is flowing faster here than here, it means that this one will have, let's call this U1, and the flow here, U2. We are saying that it will flow faster here than here, meaning that U1 will be greater than what there? U2. In this case, U1 is being greater than U2 because of the size of the pipe, not because of this. So what's affecting the velocity here is not the free flow from here, but what there? The size of the pipe. The same condition happens here. In that case, what we say, if you have different velocity, use a mean. That one there was if I have the same pipe. If for any reason I have the same pipe, and then it's unsteady, in which the velocity is changing per unit time at different sections for the same pipe, take mean velocity. But in a case like this now, usually this should flow with the same velocity there, but for the fact that here is smaller, here is bigger, here is bigger, what do you expect? Expect that velocity here should be bigger than what there, this one here, and also what there, this one here. So what is affecting the velocity here is what there, the pipe itself. Not the same there. That's what I'm thinking. Let's finish solving. We are saying that this one is smaller. So if I say that I expect U1 to have what there, a bigger value than U2 and U3. But let's have it and see. We've got U2 as this. Let's calculate for U1 and U3 and see our value. So that's the bigger concept now. Let's get U1 and U3. My thing. Yeah? Not looking at so the velocity on that pipe means the velocity in pipe 1 and that of pipe 3. Alright, so let's get for section 1. For section 1, or for pipe 1. For section 1, from the continuity equation, we have that Q is equal to A1 U1. We have this. From here, so we have that Q is equal to A1 U1. Our first task is to find A1. We know that A1 is equal to pi D1 squared all over 4. and that's equal to pi into d1 is about 0.1. That gives you 0.1 squared all over 4, and that gives you what? 0.0079 meters squared. So here's your value for A1. From here, if you make U1 some of the formula, you have that U1 is equal to Q all over A1. So divide both sides by A1, U1 becomes Q all over A1, and that's equal to Q is 0.0265, that's Q all over A1 is 0.0079. Divide these two, what do you get? 3.35. Units for discharge for velocity is meter per second. So here is velocity in pipe 1. We've gotten this already, but we were given this as 1.5. So let's get velocity for pipe 3. For section 3, do the same thing. You have that Q is equal to A3 U3. That's considering section 3. From here, our first task will be to get A3, when we know that A3 is equal to pi D3 squared all over 4, and that's equal to pi into D3 is 0.25 squared all over 4. So A3 is equal to, what do you get? 0.049 meters squared. So here's the value for A3. If we've gotten this, let's get U3. So therefore, U3 will be equal to, divide both sides by A3, I'll have Q all over A3. Substitute value, Q is equal to 0.0265 all over A3. A3 is 0.049. Divide these two, get what there? 0.54 in what's there? Meter per second. U3. So we have this. That means the velocity in the other pipes for U1 we have 3.35 meters per second, and we also have for section 3 we have 0.54 for U3. And this makes sense because we said the bigger the area of the pipe, the smaller the velocity. So it makes sense. Alright, so this one becomes 3.35 meter per second. This was given as 1.5 meter per second. This becomes 0.54 meter per second. And it makes sense because the smaller the area of a pipe, the higher its velocity. And the higher or the bigger the area, the smaller the velocity. So this is how you solve this question.